Alright guys, in this lesson we are going to be working with our parent graph shapes, but we're going to be taking data that's not perfectly on a line, and we're going to use our regression models to be able to predict using given data. So our goals are to be able to identify the appropriate regression model for a set of data, and for this lesson we're going to be dealing mostly with linear, quadratic, and exponential. So we're going to be looking for those shapes. And then also to appropriately predict using a regression model. So by the end of class, I should be able to give you a table with some real world data, and you should be able to answer questions like these 5. Alright, so this is actual data from the New York City Marathon, and these are the years of the runners and their finishing times, and those are in minutes. So to find what they were in hours, we would just divide by 60. But I want you to just analyze this table and answer these 4 questions as much as you can. One of the first things that I noticed is that as the age increases, originally the time is decreasing. So a 15-year-old is finishing in 300 minutes, a 25-year-old is finishing faster, a 35-year-old is finishing faster, but then after 35, the finishing times increase. So that's one of the things that I noticed. So what function, I want you to think about, what function would decrease and then increase? What shape would that be? Well, hopefully you were able to come up with quadratic, because as we think about, as the age increases, so as the years get bigger, it's decreasing and then it's increasing. So that's going to look like a quadratic. So how could I create an equation to best model this data? So hopefully you're thinking, I need my calculator, because that is the best way to do it. And then what age span would you feel comfortable using this model to predict? So our data goes from 15 to 65. So I would feel good about predicting any age between 15 and 65 because that's within my data. Now, I would feel comfortable predicting a little bit outside of 15, so a little bit younger than 15, and a little bit older than 65, but not too far, because then our data becomes, then the prediction becomes unreliable because we're outside of that data. All right, you have this handout. These are just refreshers. Hopefully all of these calculator steps should be somewhat familiar to you, but this is the best way to use the calculator when we are applying real world situations, because real world situations aren't going to follow a perfect model. So we're going to find the best model is what we're looking for. The first step that you always want to start with is turning your diagnostic on. And then once you've turned your diagnostic on, we've got to put the data into the calculator. Then we're going to look at the graph to see what the graph looks like so we can best choose which model to then calculate the line of best fit. So if it's linear, we're going to use StatCalc 4. If it's quadratic, we're going to use StatCalc 5. And if it's exponential, we're going to use StatCalc 0. So let's go ahead and practice with that. All right, so if you use those calculator steps, you should be able to put this data into the calculator. If you've forgotten, there's a video off to the right that you can hit play, and it walks through me putting the data in. But if you notice, we end up with that same shape that we thought, and so this is going to be quadratic, and we use the calculator to justify. I can see that decrease and then the increase. All right, so our first step is to be able to put data into the calculator and analyze the shape of the data. Check, we've done that. That's going to allow us to do both of those objectives. All right, so once I have put my data into the calculator and I looked at the stat plot to see which function fit it best, and I decided it was quadratic. So if you don't remember how to get this equation, here's a video down here that will remind you. But we're going to go ahead and write the equation that will best fit this data. So we're going to use that form y equals ax squared plus bx plus c, which should be familiar from your quadratic work in Algebra 1. So we are going to say y equals, and I would suggest that you round to 3 decimal places if it doesn't tell you otherwise. So we're going to say 0.172 x squared and then we're going to say plus, nope, it's minus because it's negative. So minus 13.714 x, and then my c is plus 451.763. So this function right here is going to fit that data, and I'm going to be able to use that to predict. All right, so we can now use the calculator to create a function to best fit the given data. All right, so here's the point of why we do it. So this is all that previous was just helping you know how to use the calculator. So now we're going to use what the calculator gives us to predict. All right, so based off of this data, the question is asking, what would we predict the running time of a 75-year-old? Well, year old, age, is going to be my x. So basically, it's asking when x is 75, what is the running time? So that's what we're looking for. That's where we're looking for y. So we're simply going to plug 75 into our function. So this is where I could go and I can say y equals 0.172 times 75 squared minus 13.714 times 75 plus 451.763. And then I can type that into my calculator. And I got 390.713 minutes. So the sentence that I'm going to write, because I want these in sentences, I want this in context, is we're going to say, according to the data, we always want to start with that. So according to the data, we would predict a 75-year-old would run the marathon in about 390 minutes. So then the next question is asking, is this reasonable? Because part of predicting is knowing if what I'm getting, if the values I'm getting are reliable or if they're reasonable. So when I look at this, my data goes from 15 to 65. So 75 is outside, so we call that extrapolating. And so I am extrapolating. I'm predicting outside of my data, but 75 is not too far out of my data. When I think about 390 minutes, so a 15-year-old running it in 300, and then we're going down, and then we're going back up. It is a lot bigger than 280 minutes, but it's not unreasonable. So I would say this is a reasonable prediction. So I said something like, this is a reasonable prediction. It's not an absurd time for finishing a marathon, and 75 years old is not too far outside my given data that it becomes unreliable. I might want to say something about I would need to see more data of older people to feel more confident. But yeah, it's a reasonable prediction. It is not too far outside. All right, so the next question is, what would you predict the running time of a 105-year-old? So I'd like you to go ahead and pause the video, and I'd like you to answer the next two questions on your own. All right, so hopefully you were able to come up with 908 minutes is what a 105-year-old according to this model. So we would use, I ran out of room, but we would use this exact same sentence. According to the data, we would predict a 105-year-old would run the marathon in about 908 minutes. All right, so is this reasonable? Absolutely not. So 105 is way too far outside of my given data to be reliable. And also common sense says that a 105-year-old is probably not running a marathon. Also, 908 minutes is 15 hours. That is not a reasonable marathon time. So those are all the ways that we're going to use these lines as far as predicting and then assessing the reliability of our prediction. All right, so we've been able to put the data in, use the calculator to create the function, and then use that function to predict appropriately. All right, so far we've graphed data, created a function, and extrapolated versus interpolate. So if you don't remember those words, extrapolate means extra or outside of, interpolate means inside of. So this is when I predict inside my data. And then this is when I predict outside. And what I mean by that is, for instance, on the last example, the data that I was given went from 15 to 65. So predicting inside my data would be predicting any age between 15 and 65. Extrapolating would be predicting outside of my data, so an age that is younger than 15 or older than 65. All right, so go ahead and have an interaction in your notes. I want you to think about these 3 things specifically. What makes sense to you? What questions do you have? What picture do you need to draw? Any sort of interaction. All right, so what I'd like you to do is I'd like you to pause the video, and here's an opportunity for you to practice on your own. So I'd like you to go through and put this data into your calculator, determine the function of best fit, and if a student studied for 15 hours, and then see if you could try this question. It's a little different, but I think you can do it. Really read carefully and figure out, what am I inputting for? And then if a student spent 100 hours. So go ahead and pause the video and try this one on your own. All right, so as you graphed the data, hopefully you were able to see that it is roughly linear. It's not perfect, but it's roughly linear. The equation that I ended up getting was y equals 25.326x plus 353.165. And so if I'm looking for studying for 15 hours, that's my x value. So I'm putting that in for x, and I'm calculating for y, and I ended up with a 733. And then down here, for the next question, it's asking if your score was 720. So that's the y value. So if y is 720, how many hours? So we're looking for x. So I'm going to plug that 720 in for y and solve for x, and I end up with about 14.5 hours of studying. And then the last question, if a student spent 100 hours studying, so hours studying is my x value. So if the 100 went in for x, what would be the expected ACT score? So we're looking for y. So according to the data, you should get an ACT score of 2885. And we realize this is unreliable because 100 is significantly outside of my collected data. There's nothing anywhere near 100 hours. So that line is going to keep going, and there will be an output for 100, but in the context of this situation, 100 is not going to make sense. And also, 2885 is not an available score. You can't get that on the math ACT. All right, so we're going to move into the second part of our objective, no longer just predicting, but now we're going to talk about the idea of the correlation coefficient, which you should have learned about in Algebra 1. If you didn't, I'm going to do just a quick review right here. So the correlation coefficient is R when we calculate any sort of regression, and we're going to use this for linear. The correlation coefficient is only going to be used for linear models. The R value is going to go anywhere between -1 and 1, and the closer it gets to 1, whether negative or positive, the closer it gets to 1, the stronger the relationship. So we call 1 perfect positive linear association, and we call -1 perfect negative linear association, just meaning that the graph is going down, and 1 means the graph is going up. So it has a positive slope, this has a negative slope. And the closer we get to 0, the less association we have. So 0 is really no linear association. So if you get an R value that's really close to 0, so either really close on the negative side or really close on the positive side, it's not a good fit. That's not a good linear association. And then usually we use about 0.75, 0.7, 0.65, somewhere in there to talk about what a good association. So 0.75 and -0.75 are strong linear associations. This is just going to be a strong positive linear association, and this is going to be a strong negative linear association. All right, so going back to your calculator, when you calculated your linear regression, it should have kicked out an R value. So if you don't have the R value on there, go ahead and go through those steps again. So we're going to stack Calc 4 and hit enter. And it should kick out an R value of 0.8716. So that's going to show up somewhere right along here, which is a strong positive linear association. So we're going to say, how strong is the fit? We're going to say this has a strong positive linear association. And then we're going to talk about that the model is a strong fit. Now, if this were a negative 8.716, it's still strong. It's just negative. So sometimes people think negative means bad, but it's not. It just means closer to a negative association. So if it's asking for you to use the correlation coefficient, that's that R value, and the closer I get to 1 or negative 1, the stronger it is. The closer I get to this middle area of 0, it's not a good fit. All right, and the last thing we're going to do as far as new learning is we're going to define each variable of the equation within the context of the data. So our equation was y equals 25.326 plus 326x plus 353.165. All right, so there are 4 parts to my equation, so I need to explain the 4 different parts. So I'm just going to quickly go through what they are. This is my output. This is my slope, or we might know it as my rate of change. X is my input. And then this is my y-intercept, or we might think of it as my initial value. And at the y-intercept, that is when x equals 0. So just a quick review of what all of those pieces are. Go ahead and write that down if you need to. All right, so the y in the context of the problem, the y represents, so it's the output, and that linear problem was kicking out ACT math score. All right, the x represents the input and what predicted ACT math score was time spent studying. All right, so then let's do our 25.326, which was our slope. So slope is always a fraction. So it's basically 25.326 something over 1. Well, it's change in y, so it's the change in the math score for every 1 hour studying. So 25.326 is the score, the increase, because it's going up, in score per additional hour spent studying. So basically it's saying that if for every extra hour that I spend studying, because I'm multiplying it by x, my score should go up about 25 points. And then the last thing is that y-intercept, or that initial value. So the 353.165 represents the score you would get if you don't study. So if we think about the initial value, or the y-intercept, we said that was when x is 0. So if x is time studying, then I should expect at least a score of 353 just based off of what I already know. So represents the score you should get with 0, I'm running out of room, hours studying. Pretend like that's what that says. So it would be the score that I should get with 0 hours studying. So if it ever asks you to interpret a linear problem, the different pieces, y and x are just input-output, this is the rate per whatever x is. So it's either going up or going down, and that's what it's increasing in context. So it's an increase in the score per additional hour spent studying, and then this is when x is 0. So if no x's have happened, so if no hours have spent studying, that is the score, the y value I should get when x is 0. All right, so we have one more situation that I'd like you to work through. You're the district manager of a coffee chain, and you're analyzing your store data to make decisions about the future of the company. The table below shows the number of new stores opened and the corresponding years. He wants to use the trend of the data to predict how many new stores they will have in the year 2019 so they can determine how many new employees to start training. So they're preparing. They're thinking, okay, so how many, according to the trend of our data, how many new stores should we have so we can start the hiring process now? So before you start typing these in, I want you to think about something. So the calculator does not know that 2010 is a year. So whenever you are typing years in, which is a lot of times, we are going to condense it and we're going to make it easy. So we always want to make the first number something simple. So when I look at 2010, I could think about X being the years since 2010. So years since 2010. So the years since 2010 would make this year 0, because years since 2010, if it's 2010, then it's 0 years since. So 2011 is going to be 1, 2012 is going to be 2, 13 is 3 years since 2010, 14, 15, 16, 17, and 18. And this is going to make our lives just a little easier when we're calculating. So if I'm thinking about the 2019, I need to think about how many years since 2000 will that be. So go ahead and pause the video, and I'd like you to answer these 4 questions. I'm sorry, these 3 questions. This one, and this one. We will work on this one in just a moment. All right, so hopefully you were able to come up with the following values. So according to the data, the company should expect to have 1,069 new stores in 2019 if this trend continues. Hopefully you notice that it's increasing, but it's kind of doubling every time, roughly, not perfect, but it's increasing at a faster rate each time. So linear would be increasing at roughly the same rate each time. Quadratic is where it's going to go up and then go down, or go down and then go up. And this is constantly going up, but it's increasing a lot faster each time. So that would put us at exponential. This would be when x is 9. And then here in 2040, if x is years since 2010, that would be 30 years. So if you put 30 into your function, you should have gotten 17 million new stores. It was a really big number. I just rounded to the nearest because it was a lot of decimals. And then which prediction is more reliable? Hopefully you were able to come up with the 2019 is more reliable because it's closer to the given data. The larger the extrapolation. So extrapolate, remember, outside of. So the further I get outside of my data, the less reliable it is. All right, so we are going to define each value of the equation within the context of the data. So hopefully you got this equation. So y equals 16.808 times 1.586 to the x. That should have been roughly the same numbers that you got for your exponential regression. Exponential regression is in the y equals a times b to the x form. So just a quick reminder, this should be review of Algebra 1, but just in case you've forgotten, y is still the output, x is still the input. All right, this is my initial value, which is still that y-intercept. So it's still when x is 0, which is kind of nice that they follow that same function. And then the 1.586, that is my growth factor. So that is what I am growing by. And if that is a number greater than 1, it's going to be growth. If it's less than 1, it's decay. Hopefully you remember that. So within the context of this, what do those different values represent? Well, the X and the Y are the easiest. X is just years since 2010, and Y is going to be the number of new stores. The 16,808 is that initial value. So that is going to represent the number of new stores they had in 2010. Because it's the initial value. So number of new stores when X equals 0, which when X equals 0, that's the year 2010. So 16, and if you notice, it actually says 14, but remember this is taking all the data and kind of making it normalized into a curve that's pretty, and so it's going to be roughly around there, but it won't be exact. And then the 1.586, that represents how fast the stores are increasing or decreasing. So that is the company is growing at a rate of 58.6%. So remember I said if it's above 1, which is 100, meaning it's keeping the same. Every year I'm adding the same amount of stores. That would be 100% versus 1.586. So if it's above 100, then it's 58.6% growth. If it was below 100, then I would get my decay from that by subtracting from 1. So 1.586 represents the company is growing at a rate of 58.6%. All right, we have done all of our objectives. Go ahead and look through these sub-objectives, see what makes sense, see where you're at, and I want you to have an interaction. So the two things we've done since our last one is interpreting values of linear and exponential functions. So what is y equals, what is x equal, what is the numbers equal, and then interpreting the correlation coefficient, so that R value. What makes sense to you? What questions do you have? All right, we are going to come up with a summary together, but in the meantime, what I want you to do is I want you to look over your notes and look at what we've just done and see if you can come up with a bulleted list of the key concepts or the important information that comes from this lesson.